A silent darkness exists that can swallow entire stars without a trace. Black holes and their mysterious hearts called singularities are the universe's ultimate puzzles, places where our understanding of physics completely breaks down. By the end of this journey, you will grasp the 30 greatest unanswered questions that keep physicists awake at night. We will confront what happens to information lost inside a black hole and ask if a wall of fire protects the edge of reality itself. Which of these cosmic secrets do you find most compelling? Our very first mystery strikes at the heart of physics itself. The information paradox asks a deceptively simple question. What happens to the information about an object when it falls into a black hole? Think about a book tossed into a fire. The book burns, but the information it contained, the words and the story, is not truly destroyed. It is transformed into smoke and ash. In principle, a physicist with a perfect understanding of the laws of nature could reverse the process and reconstruct the book from the ashes. This is a fundamental rule of quantum mechanics. Information, the specific arrangement of what makes something what it is, can never be truly lost. It can only be scrambled. But a black hole presents a terrifying exception to this rule. When something crosses the event horizon, it seems to be erased from the universe forever. The information about that object, whether it was a star, a spaceship, or a library, appears to vanish without a trace. This is the paradox. Stephen Hawking first highlighted this conflict. He calculated that black holes should slowly evaporate over astronomical timescales, eventually disappearing in a final burst of radiation. But this Hawking radiation, he argued, would be completely random. It would carry no information whatsoever about what fell in. The black hole would evaporate, leaving behind only generic heat, and the original information would be permanently destroyed. This conclusion sent shockwaves through the physics community. It meant our two most successful theories, general relativity and quantum mechanics, could not both be correct. For decades, this paradox divided scientists. Was information truly lost, forcing us to rewrite quantum theory, or was it somehow preserved, challenging our understanding of black holes? The debate raged, a silent war of ideas over the fate of reality itself. This paradox forces us to peer deeper into the very heart of the darkness itself. The ultimate enigma is not the black hole's edge, but what lies at its core. This is our second great mystery, the nature of the singularity. According to Einstein's theory of general relativity, every black hole contains a singularity at its center. This is not a physical object you could touch. It is a point of infinite density where all the mass that has ever fallen into the black hole is crushed into a volume of zero size. Think of it as a cosmic dead end for mathematics and physics. The equations of relativity, which so beautifully describe the curvature of spacetime and the force of gravity, simply output a division by zero error. The numbers become meaningless, infinity appears on the page, and our understanding of reality grinds to a halt. At the singularity, the fabric of spacetime itself is torn apart. The very concepts of here and there, of before and after, cease to have any meaning. It is a place where the pull of gravity becomes infinite, a force so unimaginably strong that not even a single particle of light could resist it. To visualize this, picture a grid representing the universe with lines for space and time. As you approach a black hole's center, the grid lines are pulled tighter and tighter, like a rubber sheet stretched to its absolute limit. At the singularity, the grid does not just bend, it rips completely. The sheet is torn, and we have no physics to describe what exists on the other side of that tear. So what truly lies at the center? Is it a gateway to another universe, a point of new creation? Or is it simply the final full stop at the end of a sentence, a place where existence itself is erased? The singularity is the ultimate blank spot on our map of reality, a silent scream from the universe that our current knowledge is incomplete. But what if the black hole's edge is not a silent threshold, but a place of violent, fiery death? This is the third great mystery, the firewall paradox. It is a terrifying and controversial idea that suggests a literal wall of fire might exist at the event horizon, ready to incinerate anything that tries to cross. Imagine falling toward a black hole. According to Einstein's theory, you should feel nothing special as you pass the point of no return. The event horizon is a one-way street in space-time, but it should not be a physical barrier. You would be peacefully, if tragically, pulled inward, but the firewall theory paints a very different picture. In this scenario, you would not pass through smoothly. Instead, you would be instantly vaporized by an unimaginably intense wall of energy the moment you touched the horizon. This fiery barrier would destroy you and all the information you carry long before you reach the mysterious singularity at the center. This radical idea did not come from nowhere. It emerged from physicists desperately trying to solve the information paradox. They realized that if information is not lost, then it must somehow be encoded in the Hawking radiation leaking from the black hole. But for that to work, the radiation just outside the event horizon must be entangled with the radiation far away. This creates a problem. That same radiation near the horizon must also be entangled with the particles that fell inside long ago. This double entanglement is forbidden by the rules of quantum mechanics. It is like a secret that can only be shared with one person. You cannot share it with two without breaking a fundamental trust. To resolve this contradiction, the theory suggests that the entanglement must be violently broken at the horizon itself. This severing of quantum links would release a catastrophic amount of energy, manifesting as the deadly firewall. This proposal has sparked intense debate. To many, it feels like a betrayal of Einstein's greatest insight, the principle that a free-falling observer should not notice anything unusual at the event horizon. A firewall makes the horizon a special, violent place, rewriting one of the core tenets of general relativity, so we are left with a disturbing choice. Do we accept a peaceful horizon and lose information forever, breaking quantum theory? Or do we save information by creating a wall of fire, breaking Einstein's theory? The firewall paradox leaves us staring into the abyss, forced to question which of our most cherished physical laws must be sacrificed at the edge of a black hole. Accepting the firewall paradox means surrendering the very idea of crossing the horizon. But what if you could? What if you somehow survived the passage and journeyed inward past the point of no return? The fourth mystery dares to ask what truly lies inside a black hole. General relativity gives us a bleak forecast. Once inside, every path leads relentlessly downward toward the crushing singularity. There is no stopping, no turning back. Space-time itself is falling inward faster than the speed of light, dragging everything with it. You would be caught in a cosmic river, flowing toward a waterfall from which there is no escape. Yet many physicists suspect that Einstein's equations are telling only half of the story. One of the most captivating possibilities is that a black hole is not a dead end but a bridge. The singularity at its heart might not be a point of destruction but a tunnel to somewhere else entirely. This theoretical passage is known as a wormhole. Imagine the black hole as a mountain, but instead of a solid core, it contains a hollow tunnel that punches straight through to the other side. This wormhole could connect two distant parts of our own universe, or something even more incredible. It could be a gateway to an entirely different cosmos, a universe parallel to our own. You would fall in one side and emerge who knows where, perhaps in a reality with different laws of physics, or in a younger, hotter universe just beginning its life. Another wild theory suggests the interior of a black hole is not a tunnel but a cradle. What if the immense pressure and energy at the core does not just destroy matter but transforms it? Some speculative models propose that a black hole could contain an entire new universe, budding off from our own like a seed. In this view, our entire cosmos, with its billions of galaxies and trillions of stars, could itself be the interior of a black hole existing in a parent universe. This creates a dizzying, infinite regress of universes within universes, each born from the heart of a cosmic giant in another reality. So as you fall through the darkness, are you heading toward obliteration, or are you a pioneer on the verge of the greatest discovery imaginable? Is the black hole a tomb or a womb? We simply do not know. The interior remains the ultimate locked room mystery, a place where our physics fails and our imagination is the only tool we have left. The sheer scale of these cosmic puzzles is almost impossible to grasp. Lurking at the center of nearly every galaxy, including our own Milky Way, rests a gravitational monster so immense it defies easy explanation. This is the fifth great mystery, the origin of supermassive black holes. These are not the stellar mass black holes formed from collapsing stars. These are behemoths weighing millions, even billions of times more than our Sun. The deepest puzzle is not just their size, but their age. Our most powerful telescopes have found these giants shining brightly in the universe's infancy, when the cosmos was less than 1 billion years old. This presents a monumental challenge. How did they get so big so fast? A black hole can only consume matter at a certain rate, a limit called the Eddington limit. It is like trying to fill a swimming pool with a garden hose. For a supermassive black hole to reach its observed size in such a short cosmic time, it would have needed to feast at or above this maximum rate for its entire existence, a scenario that seems highly unlikely. So how did they do it? Scientists have two leading theories, and both push the boundaries of our understanding. The first idea is that they started from smaller seeds. Perhaps the first generation of stars were colossal, hundreds of times more massive than our Sun. When these titanic stars died, they would have left behind black hole seeds far larger than any forming today. These heavy seeds then merged together and voraciously consumed the dense gas surrounding them in the early universe, growing at a breakneck pace to become the giants we see. The second theory is even more dramatic. It suggests that these supermassive black holes did not start from stars at all. Instead, vast clouds of primordial gas under their own immense weight could have collapsed directly into a black hole, bypassing the star-forming stage entirely. Imagine a giant gas cloud, thousands of light years across, suddenly and catastrophically giving birth to a black hole weighing tens of thousands of solar masses from its very first breath. This direct collapse would provide a massive head start, a ready-made giant that could then grow to even more staggering proportions. Yet both theories face their own difficulties. The environment for a direct collapse would have to be just right, with no heavy elements to fragment the cloud and no nearby stars to disrupt it. And for the seed theory, the growth rates required are still incredibly demanding. The existence of these ancient giants is a cosmic clue, a fossil record telling us that the early universe was a far more violent and extreme place than our standard models predict. They are a direct challenge to our story of cosmic evolution, forcing us to ask what incredible forces were at play in the dawn of time to forge such impossible objects. Our journey into the black hole's heart revealed a terrifying truth, a singularity cloaked in absolute darkness. But what if that cloak could be torn away? The sixth mystery confronts us with the possibility of a naked singularity, a cosmic monster stripped of its event horizon. Imagine a point of infinite density where gravity becomes infinite and physics breaks down. But now imagine it exposed to the rest of the universe for anyone to see. Such an object would be the most dangerous and unpredictable thing in existence. Most physicists are deeply skeptical, clinging to a principle called cosmic censorship. This is the hopeful idea that the laws of physics act as a cosmic censor, always ensuring that every singularity is decently clothed behind an event horizon, forever hidden from our view. This censorship protects the universe from the chaos a naked singularity would unleash. Without an event horizon, the unfiltered insanity of the singularity would be able to influence the world outside. The very fabric of cause and effect could unravel. In a universe with naked singularities, you could theoretically witness your own future being rewritten or see an effect precede its cause. The fundamental predictability that allows science to function would vanish. So why do we even entertain this terrifying idea? Because our equations sometimes suggest it might be possible. If a black hole rotates fast enough or carries a powerful enough electric charge, the mathematics of general relativity indicates that the event horizon might shrink away to nothing, leaving the singularity bare for all to see. It is a theoretical loophole, a set of perfect and perhaps impossible conditions where the cosmic sensor fails to do its job. The implications are staggering. A naked singularity would be a gateway to the laws of physics themselves, a place where we could directly observe the breakdown of our theories and perhaps glimpse what lies beyond. It would be a natural laboratory for a theory of quantum gravity, offering a front-row seat to the universe's most fundamental workings. But the price of that knowledge could be the complete dissolution of reality as we understand it. The hunt for these exposed monsters is more than an academic exercise. It is a quest to determine whether the universe is fundamentally orderly, keeping its most dangerous secrets locked away, or if it allows for pure, unshielded chaos. Are the laws of physics a perfect set of rules that always protect causality, or are there cracks in the cosmic armor where true madness can leak out? Crossing the event horizon is only the beginning of the end. From that point onward, the fate of any matter is sealed by the black hole's overwhelming gravity. The first dramatic transformation is a process with a vivid name, spaghettification. Imagine an astronaut falling feet first toward the singularity. The pull of gravity on their feet is exponentially stronger than the pull on their head. This difference in force, known as a tidal force, stretches them lengthwise into a long, thin stream of atoms. At the same time, the immense pressure from the side squeezes them inward, compressing them from all directions. The unfortunate astronaut would be simultaneously stretched into a strand and compressed into a thread, resembling a piece of spaghetti. This is not a gentle process, but a violent, fundamental reshaping. For a stellar mass black hole, this spaghettification would happen well outside the event horizon, tearing an object apart before it even crossed the threshold. But for a supermassive black hole with a more gentle gravitational gradient, you might actually pass through the event horizon intact, only to be spaghettified deep within the interior. As this stream of particles continues its inward plunge, the mysteries only deepen. What happens next to this stretched-out matter as it nears the singularity itself? Some theories suggest it is simply crushed out of existence, its structure utterly erased as it adds to the infinite density of the central point. Other ideas propose that the matter is shredded into its most fundamental components, a soup of particles and energy that no longer resembles anything we would recognize. The final moments before the singularity are a complete blank. Our physics offers no guide, no prediction for the ultimate state of being. Does the matter cease to be matter entirely, becoming pure energy or something else entirely? Does it cross a boundary into another realm of physics we cannot yet describe? The journey from a structured object to a stream of atoms to an unknown final form is one of the most profound transformations in the cosmos, and its final step remains one of the universe's most guarded secrets. This stretched-out matter, shredded into its most fundamental components, represents a state of ultimate chaos. Yet, remarkably, black holes themselves seem to possess a precise measure of this chaos, a quantity known as entropy. In the everyday world, entropy is a measure of disorder. A tidy room has low entropy, while a messy room has high entropy. The second law of thermodynamics states that the total entropy of the universe always increases, moving from order to disorder. This is why a hot cup of coffee cools down, its heat dispersing into the room, never spontaneously gathering back into the cup. For the longest time, physicists saw a black hole as the ultimate entropy sink, a cosmic vacuum cleaner that simply made things disappear, seemingly reducing the universe's disorder. This changed in the 1970s when a young physicist named Jacob Bekenstein made a bold proposal. He argued that a black hole must have entropy and a tremendous amount of it. This was a revolutionary idea. If a black hole has entropy, then it also must have a temperature, and anything with a temperature must emit radiation. Stephen Hawking initially disagreed, but his own calculations soon proved Bekenstein correct, leading to the discovery of Hawking radiation. The real shock came from the formula they developed. The Bekenstein-Hawking formula states that a black hole's entropy is proportional to the area of its event horizon. Think of the event horizon as the black hole's surface. The amount of information or disorder a black hole contains is not related to the volume of space inside it, but only to the two-dimensional area of its spherical boundary. This is profoundly counterintuitive. Imagine you have a box. The number of different ways you can arrange the objects inside the box, its entropy, should depend on the box's volume, the amount of three-dimensional space available. A bigger box can hold more things in more arrangements, but a black hole defies this logic. A black hole with twice the radius has 8 times the volume inside. Yet its entropy only increases by a factor of 4 because the area of its surface only quadruples. It is as if all the intricate information about everything that ever fell in, every star, every planet, every book, is not stored throughout the vast interior volume, but is instead painted onto the two-dimensional surface of the event horizon like a cosmic hologram. This discovery hints at one of the most radical ideas in all of physics, the holographic principle. It suggests that our perception of a three-dimensional universe might be an illusion, a holographic projection from information stored on a distant two-dimensional surface. The black hole entropy enigma forces us to ask if we are all just shadows on a wall, a magnificent cosmic projection whose source code is written on the boundary of space itself. This holographic surface where information might be stored is not a static wall. It is alive with a faint, ghostly energy. Stephen Hawking's most famous insight revealed that black holes are not eternal prisons. They slowly leak, emitting a faint glow of radiation that carries away their mass particle by particle. This Hawking radiation is the reason black holes can eventually evaporate, vanishing from the universe over astronomical timescales. The mechanism for this is one of the most bizarre consequences of quantum theory. Empty space is not truly empty. It is a seething sea of virtual particles, pairs of particles and antiparticles that constantly pop into existence, borrow energy from the vacuum, and then annihilate each other almost instantly, repaying the energy debt. This quantum froth happens everywhere all the time, but at the edge of a black hole, something extraordinary can occur. If one of these virtual particle pairs appears right at the event horizon, gravity can tear them apart. One particle falls into the black hole while the other escapes into space. The escaped particle becomes real, stealing a tiny amount of the black hole's energy to pay its debt to the universe. From the perspective of a distant observer, the black hole has just emitted a particle. This slow, relentless leakage is Hawking radiation. The black hole pays for this escape with its own mass, slowly shrinking over eons. Yet this elegant solution creates a new and profound puzzle. Hawking's original calculation suggested this radiation was completely random, a featureless thermal glow. It would be like the heat coming from a stove, telling you nothing about the pot that was placed on it. This randomness is at the heart of the information paradox we encountered earlier. If the radiation is purely thermal, then all the unique information about what fell into the black hole is lost forever when the hole evaporates. But if quantum mechanics is correct, that information must be preserved. This leads to the unresolved core of the mystery. What is the true nature of this radiation? Is it truly random, or does it contain subtle, encoded imprints of every star and atom that ever crossed the horizon? The precise spectrum of Hawking radiation, its exact energy signature, holds the answer. Detecting that faint whisper against the roaring background of the cosmos is one of the greatest experimental challenges in physics. We have never directly observed Hawking radiation, and until we do, we cannot know if it is a simple funeral dirge for a dying black hole, or a complex song containing the entire history of everything it ever consumed. Hawking radiation slowly chips away at a black hole's immense mass over trillions of years, but the final act is anything but slow. As the black hole shrinks, its temperature rises and the rate of radiation accelerates in a runaway feedback loop. In its last second of existence, a black hole with the mass of a small mountain would release more energy than all the stars in the observable universe combined. It would be a flash of unimaginable intensity, a cosmic firework signaling the end of an era. But what does this final burst actually contain? Is it a pure, white-hot eruption of particles and light, or is it something far more complex? The greatest puzzle is whether this explosion perfectly encodes the entire history of the black hole, finally releasing the information trapped within, or if it is just a final, random shriek into the void. And when the flash fades, what remains? Does the black hole vanish completely, leaving behind only empty space? Or does it leave a relic, a tiny, stable fragment no larger than the Planck length, the smallest possible size in the universe? This hypothetical remnant would be a fossil of pure information, a crystal of spacetime itself, too small and dense to ever evaporate further. Yet such an object would itself be a singularity, presenting all the same problems of infinite density we started with. The ultimate fate of a black hole forces us to confront the nature of nothingness itself. Does complete evaporation mean a return to perfect vacuum, or does it leave a permanent scar on the fabric of the cosmos, a ghostly imprint of what once was the darkest object in existence? That final explosive flash pushes our theories to their absolute limit. But what if we could create black holes right here on Earth? This leads us to the 11th mystery, a puzzle that connects the cosmic vastness of gravity to the infinitesimal world of quantum particles. The hierarchy problem asks why gravity is so unbelievably weak compared to the other fundamental forces. The electromagnetic force that holds atoms together is stronger than gravity by a factor of 1 followed by 36 zeros. To feel the pull of a magnet lifting a paperclip, you must overcome the gravitational attraction of the entire planet Earth beneath you. This staggering difference in strength is one of physics' deepest embarrassments. Some theories, like string theory, suggest a possible solution. They propose that gravity only appears weak because it is not confined to our three-dimensional universe like the other forces. It could be leaking into extra, hidden spatial dimensions that are curled up too small for us to perceive. This leakage would dilute gravity's strength, explaining its feebleness in our world. This idea has a breathtaking consequence. If these extra dimensions exist, then the energy required to create a black hole could be dramatically lower than we once thought. We could potentially manufacture them ourselves. These would not be the stellar giants of deep space, but microscopic black holes smaller than an atom. Imagine the most powerful particle accelerators, like the Large Hadron Collider, smashing protons together at nearly the speed of light. In these violent collisions, for a fleeting instant, the energy could be concentrated into a volume so small that it warps spacetime into a tiny knot of immense density, a quantum black hole. These microscopic entities would be utterly unlike their cosmic cousins. They would not live for eons, but would evaporate almost instantly in a burst of Hawking radiation, lasting perhaps only a millionth of a billionth of a billionth of a second. Their fleeting existence would be the ultimate experimental test. Detecting the specific signature of their explosive decay would be the first direct proof of Hawking radiation, confirm the existence of extra dimensions, and solve the hierarchy problem in one stunning blow. Yet, despite our most powerful machines, we have not found them. their continued absence is as telling as their discovery would be. It forces us to question the very architecture of reality. Are we looking in the wrong place, or is our universe simply not built with these extra dimensions? The search for micro-black holes is a hunt for the hidden geometry of the cosmos, a quest to discover if the fabric of space has more folds and creases than we can possibly see. Gravitational waves have torn open a new window onto the cosmos, allowing us to witness its most violent events. Among the signals captured by observatories like LIGO and Virgo, the most tantalizing are the collisions between a black hole and a neutron star. These encounters are not just cosmic crashes, they are profound experiments in extreme physics, forcing us to ask what happens when an unstoppable force meets an almost immovable object. A neutron star is the incredibly dense corpse of a massive star, a city-sized object so compact that a single teaspoon of its material would weigh billions of tons. It is matter pushed to its absolute limit, a giant atomic nucleus held up by quantum forces against its own immense gravity. When a black hole enters the picture, this delicate balance is shattered. The central mystery of these collisions lies in the final, frantic moments. Does the black hole simply swallow the neutron star whole in a single, silent gulp, or does it tear the star to shreds first? The answer is written in the gravitational waves and the potential flash of light that follows. If the black hole is large enough, its tidal forces are overwhelming. The neutron star would cross the event horizon intact, vanishing without a trace. The gravitational wave signal would simply cease, a clean and abrupt end to the cosmic dance. But if the black hole is smaller and the dance is tighter, the outcome is far more spectacular. In this scenario, the black hole's gravity would stretch and squeeze the neutron star, ripping it apart just outside the event horizon. The star would be shredded into a swirling, incandescent disk of debris, a whirlpool of the universe's most extreme matter. This tidal disruption would release a cataclysmic explosion of light across the electromagnetic spectrum, a brilliant firework alongside the rumble of gravitational waves. For scientists, the debris from such a disruption is the real prize. It is a natural laboratory for studying matter at densities impossible to create on Earth. We do not know what happens to the components of atoms when they are subjected to such unbearable pressure. Do the neutrons themselves break down into a soup of even more fundamental particles called quarks, creating a strange new state of matter? Or does something even more exotic emerge? Every collision we detect is a data point, a clue that helps us map the equation of state for nuclear matter, the very law that dictates how matter behaves under these insane conditions. Each ripple in space-time and each accompanying flash of light brings us closer to understanding the fundamental building blocks of reality, forged in the violent death throes of a star. These cosmic geysers of energy defy the very darkness from which they erupt. While a black hole pulls everything in at its equator, it can simultaneously fire out two narrow, blisteringly fast jets from its poles. These are not random sprays, but incredibly focused beams of matter and radiation, shooting across thousands of light years at almost the speed of light. They are cosmic blowtorches, powerful enough to punch through entire galaxies and influence the formation of stars far beyond their own domain. The central mystery is not their existence, but their origin. How can a region defined by its voracious appetite become the universe's most powerful engine of ejection? The secret lies just outside the event horizon, in the chaotic whirlpool of superheated gas and dust known as the accretion disk. Material here is spiraling inward at fantastic speeds, creating a maelstrom of friction and magnetic fields. This disk acts as the powerhouse, but it alone cannot create such a focused beam. Think of it as a raging bonfire, hot and energetic, but its heat radiates in all directions. To turn that bonfire into a laser beam, you need a lens and a nozzle. For a black hole, that nozzle is its own ferocious rotation and the magnetic fields tangled within the disk. As the black hole spins, it drags the fabric of spacetime around with it, twisting the magnetic field lines into tightly wound coils. These coils become a kind of cosmic particle accelerator, channeling some of the infalling material and launching it outward along the path of least resistance, which are the black hole's rotational poles. This creates the two opposing jets, yet the precise mechanics of this launch remain one of astrophysics' biggest puzzles. We do not know exactly how much energy is extracted from the black hole's spin versus the accretion disk itself. We do not fully understand how the magnetic fields remain so stable and focused over such vast distances, and we cannot explain why some black holes produce these immense jets while others, seemingly identical, remain quiet. These jets are a testament to the raw, untamed power of gravity and magnetism working in concert, a violent reminder that even in the deepest darkness, the universe finds a way to scream its presence across the void. These cosmic jets scream with complexity, yet the black holes that power them are described by a theory of stunning simplicity. This is the no-hair theorem. It suggests that a black hole, for all its terrifying power, is fundamentally bald. It possesses no intricate features, no distinguishing details, no personality. According to this elegant idea, you can describe any black hole in the entire universe with just three numbers: its mass, its electric charge, and its spin. Everything else, every single detail about the objects that fell in, is permanently erased. It does not matter if the black hole formed from a collapsing star made of hydrogen or from a billion planets made of gold and diamonds. Once the material crosses the event horizon, the black hole forgets it all. All that remains is how heavy it is, how much it is spinning, and whether it has a net electric charge. This is the ultimate act of cosmic simplification. A black hole has no memory. It is the universe's most efficient shredder, not just of matter, but of information itself. To understand this, imagine two completely different objects, a sphere of pure iron and a complex sculpture of ice. You toss both into a blazing furnace. After the fire burns out, all you have left is the same pile of warm ash. You cannot tell what the original objects were. The no-hair theorem suggests a black hole does the same thing, but with spacetime itself. It melts down everything into a perfect, featureless gravitational field defined only by those three simple numbers. But is this truly the whole story? Recent discoveries are tugging at this elegant baldness, suggesting black holes might have subtle hair after all. When two black holes spiral together and merge, the resulting single black hole does not settle down instantly. It rings like a bell, vibrating in a process known as ring-down. The frequencies of these vibrations are supposed to be determined solely by its final mass and spin, according to the no-hair theorem. But what if careful analysis of the gravitational waves from these collisions reveals tiny deviations, faint overtones in the ringing that cannot be explained by mass and spin alone? These subtle signals would be the hair, the hidden complexity that the theorem claims cannot exist. This hair would not be a physical fuzz on the surface. It would be a permanent imprint in the gravitational field, a memory of how the black hole was born or what it has consumed, etched into the very fabric of spacetime around it. Finding it would force a dramatic rewrite of our understanding. It would mean black holes are not the simple, forgetful objects we thought they were. They would have a hidden history, a secret identity written in gravity itself. The hunt for this gravitational hair is on, a meticulous search through the faintest ripples in spacetime for the proof that even the darkest objects in the universe cannot fully hide their past. This cosmic balance between the infinite and the infinitesimal leads us to a mystery that connects the very small to the very large. The vacuum of space is not empty, it is a seething ocean of quantum energy. According to our best calculations, the energy of this vacuum should be immense, generating a repulsive force so powerful that it would have ripped the universe apart moments after the Big Bang, preventing stars, galaxies, or life from ever forming. Yet when we look out at the cosmos, we see a very different story. The universe is expanding at an accelerated rate, driven by a faint, smooth, repulsive force we call dark energy, whose strength is represented by the cosmological constant. The puzzle is that the calculated vacuum energy is 120 orders of magnitude stronger than the observed dark energy. That is a 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the entire history of science. This is where black holes enter the stage, not as destroyers, but as potential cosmic regulators. One radical idea suggests that black holes, through their immense entropy, might be acting to smooth out and neutralize the violent quantum frenzy of the vacuum. The sheer amount of information stored on their event horizons could be averaging out the vacuum's wild fluctuations, leaving behind only the tiny, residual force we observe as dark energy. It is a cosmic feedback loop where the structure of the universe in the form of black holes tunes the very energy that governs its expansion. This creates a breathtaking and perhaps suspicious coincidence. Why is the energy of the vacuum so perfectly tuned to allow for our existence? Is it just a lucky accident, or is there a deeper principle at work? A principle where black holes are not just inhabitants of the cosmos, but essential architects, quietly maintaining the delicate balance that makes everything possible. This conflict between preservation and destruction brings us back to the firewall with terrifying precision. The AMPS thought experiment, named for its creators Olmary, Marolf, Polchinski, and Sully, is not just a theory, it is a trap for physics. It forces us to choose between 3 deeply held beliefs, and one of them must be wrong. The 3 statements seem unassailable. First, information is not lost, it escapes a black hole encoded in the Hawking radiation. Second, physics is local, meaning an event at one point in space cannot instantly influence another point far away. And third, an observer crossing the event horizon should experience nothing special, no fiery drama, just the smooth continuation of their fall. The AMPS argument proves you cannot have all 3. It is a cosmic catch-22. To see why, picture an astronaut named Alice bravely approaching an old, evaporating black hole. She carries with her a perfect quantum bit, a qubit of information. Just outside the horizon, she collects a piece of the early Hawking radiation, call it particle A. According to the no information loss postulate, this particle A must be entangled with another particle B that escaped much earlier. Their quantum states are linked, a perfect pair. But here is the catch. For information to be saved, particle A must also be entangled with a different partner, particle C, which is the counterpart to Alice's qubit that fell inside long ago. This creates an impossible situation. Particle A cannot be maximally entangled with both particle B outside and particle C inside. It would be like a secret shared with 2 different people, with each believing they are the only one who knows. In the quantum world, such promiscuous entanglement is strictly forbidden by a principle known as the monogamy of entanglement. So, to save information, the entanglement between A and B must be broken. But severing this quantum link is a violent act. It releases a firestorm of energy, manifesting as the deadly firewall at the horizon. Alice is incinerated the moment she arrives. This preserves information but shatters the principle that the horizon is uneventful. The alternative is to let Alice pass through peacefully, but then the entanglement between A and B remains, and the information inside is lost forever. We are left with a brutal choice: burn up the astronaut or destroy quantum mechanics. There is a potential escape route from this trap, a concept known as black hole complementarity. This mind-bending idea suggests that both stories are true, but for different observers. From the perspective of someone like Alice falling in, she passes smoothly through the horizon, and the information she carries falls inward with her. But from the perspective of an outside observer watching from a safe distance, that same information is scrambled and reflected at the event horizon, encoded into the Hawking radiation. In this view, there is no single objective reality. The experience of the infalling astronaut and the record of the distant observer are both valid, complementary descriptions of the same event. They cannot be compared because no one can be in both places at once to report the contradiction. It is as if the universe has a built-in censorship rule, preventing anyone from seeing the paradox firsthand. Yet this solution feels deeply unsettling. It challenges our most basic assumption about reality, that things happen in one definite way. If complementarity is correct, then the information is both inside the black hole and outside it at the same time, a clear violation of the no-cloning theorem in quantum mechanics. The very concept of a single, shared universe begins to blur. Are we forced to accept that reality is fundamentally observer-dependent, that the fate of information depends on who is asking the question? The Amps firewall and the principle of complementarity leave us staring into a philosophical abyss, questioning whether the universe itself can keep a consistent story when faced with its own most extreme creations. This paradox of complementary realities forces us to consider an even more radical cosmic mirror. If a black hole is a one-way door into darkness, what lies on the other side? The 17th mystery dares to propose an answer, the white hole hypothesis. A white hole is the theoretical opposite of a black hole in every conceivable way. Where a black hole's event horizon is a point of no return, a white hole's horizon is a point of no entry. Nothing can ever cross inside. Instead, matter and energy can only pour outward, erupting from its core in a relentless, unstoppable fountain. Think of it as a cosmic geyser, spewing out light and material into the universe, while completely sealed against any influence from the outside. The mathematics of general relativity allows for such an object. In fact, if you mathematically reverse the flow of time in the equations for a black hole, you get a white hole. It is a perfectly valid, if bizarre, solution to Einstein's field equations. But mathematical possibility does not guarantee physical existence. The central problem with a white hole is its profound instability. It violates the second law of thermodynamics by seemingly creating order from nothing, spewing out organized energy without any apparent source. Furthermore, any single particle of dust or photon of light falling onto a white hole's horizon would carry energy, and according to relativity, that energy would warp spacetime, potentially causing the white hole to collapse instantly into a black hole. For it to exist, it would have to be a perfect, pristine object in a universe that is inherently messy and interactive. So if they are so improbable, why do physicists still entertain the idea? One captivating possibility connects them to the very beginning of everything. What if the Big Bang itself was the ultimate white hole event? Our entire observable universe, with all its galaxies and stars, could be the material erupting from a primordial white hole singularity, a single point of creation pouring forth reality itself. Another, even more speculative, theory suggests that a white hole is not a separate object but the other end of a black hole. When you fall into a black hole, you are not crushed into a singularity, but are instead ejected through a white hole into another universe or a different part of our own. This would turn every black hole into a tunnel, a one-way bridge between realities. Yet, despite these alluring ideas, no astronomical observation has ever found a convincing candidate for a white hole. We see things falling into black holes, but we never see cosmic fountains of energy with the precise properties a white hole would demand. They remain a beautiful thought experiment, a haunting ghost in the machinery of our equations. They challenge us to ask if every possible solution written in the language of mathematics must exist in the physical world, or if the universe is more selective, forbidding certain marvels to preserve its own consistent laws. Perhaps the most elegant escape from the firewall trap lies in a concept so profound it unifies two of the greatest puzzles in physics. The ER equals EPR conjecture dares to propose a breathtaking connection between the spooky world of quantum entanglement and the very fabric of spacetime. The letters EPR come from a famous thought experiment by Einstein, Podolsky, and Rosen, who used quantum entanglement to argue that quantum mechanics must be incomplete. Entanglement is that strange phenomenon where two particles can be linked across any distance, instantly mirroring each other's states. Einstein called it spooky action at a distance, deeply troubled by the implication of faster-than-light communication. The letters ER, on the other hand, come from Einstein and Nathan Rosen, who discovered that the equations for a black hole could be extended to form a bridge between two distant points in space, a wormhole. For decades, these two ideas, EPR entanglement and ER wormholes, were seen as completely separate, one belonging to quantum mechanics and the other to general relativity. The revolutionary conjecture suggests they are not just similar, they are exactly the same thing. Every pair of entangled particles is not communicating mysteriously across a void. They are connected by a microscopic wormhole, a tiny bridge in the fabric of spacetime itself. This is not a metaphor, it is a potential fundamental description of reality. Quantum entanglement is the physical manifestation of a geometric link. Think of two sheets of paper representing different locations in space. A wormhole is like a tightly rolled tube connecting them, a shortcut through a higher dimension. The ER equals EPR idea says that entangled particles are like points on those two sheets, linked by that invisible microscopic tube. Their instantaneous connection is not magic, it is geometry. They are simply next to each other through a hidden fold in the universe. This radical idea offers a stunningly beautiful solution to the information paradox. Remember the problem of the entangled Hawking radiation pairs. One particle falls in while its partner escapes. The conjecture reframes this entire drama. It suggests that the particle that falls into the black hole and the particle that escapes are not two separate entities with a broken quantum link. They are connected by one of these microscopic wormholes. The interior of the black hole is not an isolated prison. It is spatially connected through a vast web of these tiny bridges to all the Hawking radiation that has ever leaked out. The information about what fell in does not need to be mysteriously encoded on the horizon or violently released by a firewall. It simply takes a different path, traveling through these hidden wormhole connections to re-emerge with the outgoing radiation. The information was never truly lost inside, it was just taking a cosmic shortcut home. This vision weaves quantum mechanics and gravity into a single, seamless tapestry. It tells us that the spookiness of the quantum world and the warped geometry of spacetime are two sides of the same coin. The universe is not built with separate rules. It is a single, interconnected network where information and geometry are inextricably linked. The deepest layers of reality may be a labyrinth of unseen connections, where every entangled pair is a whisper of a hidden tunnel, and every black hole is a grand central station in a cosmic subway system we are only just beginning to map. The elegant geometry of wormholes offers a beautiful escape from the information paradox, but the battle to solve it has only intensified with new mathematical weapons. Recent developments have pushed the conflict into a strange and fertile new territory, reshaping the debate with powerful tools from quantum gravity. One of the most promising modern approaches involves calculating black hole entropy using gravitational path integrals, a complex method that sums over every possible history of spacetime to find the most probable outcome. Within this framework, a startling concept has emerged, the island rule. Picture the event horizon not as a definitive boundary, but as a shoreline. According to this rule, as a black hole evaporates and its entropy is calculated, regions inside the event horizon, dubbed islands, can suddenly contribute to the total. It is as if you are trying to measure the complexity of a coastline from a satellite, and you discover that hidden coves and inlets previously invisible to you must be included in the measurement to get the correct answer. These islands are not physical places you could visit, but mathematical regions that emerge from the calculation. suggesting that the information swallowed by the black hole is not imprisoned at its core. Instead, it is somehow connected to the Hawking radiation streaming out via these enigmatic quantum bridges. The radiation is not random after all. It carries a subtle, encoded diary of everything that fell in, with the islands acting as a kind of cosmic switchboard facilitating the transfer. This does not mean we can easily read that diary. The process is fantastically complex and occurs across timelines that boggle the mind. Yet, the island rule provides a concrete, calculable pathway to preserve information without violating other sacred principles. It suggests that the interior of the black hole and the exterior radiation are not separate worlds, but a single, deeply connected quantum system. The event horizon becomes a fuzzy, quantum boundary rather than a sharp, classical wall. These new tools are offering a compromise in the long-standing war between general relativity and quantum mechanics, hinting that information escapes not by being burned at a firewall or by taking a wormhole shortcut, but through a gradual quantum teleportation process woven into the very fabric of evaporating spacetime. The paradox is not yet fully solved, but for the first time we have a map that shows a possible route through the labyrinth, a map written in the language of islands and emergent connections. The hunt for these hidden cosmic connections leads us back to the very beginning of everything. The 20th mystery asks if the first black holes were not born from dying stars, but from the violent birth pangs of the cosmos itself. These hypothetical objects are known as primordial black holes, and they could rewrite our understanding of the universe's composition. Imagine the universe in its first fleeting moments, a seething, dense, and incredibly hot soup of energy. Within this chaotic froth, random fluctuations in density could have been so extreme that pockets of space simply collapsed under their own intense gravity, pinching off to form black holes. This would have happened in the first second of existence, long before the first stars ever ignited. The fascinating proposition is that these ancient relics might still be with us today, and they could solve one of astronomy's greatest puzzles, the nature of dark matter. We know dark matter exists because its gravitational pull guides the motion of galaxies, but we have never directly detected what it is made of. Primordial black holes are a compelling candidate. They are cosmic ghosts massive enough to exert a gravitational pull, yet potentially small enough to have evaded detection for billions of years. They could be drifting through our galaxy by the trillions, invisible and unnoticed. But how do you find something that emits no light? Astronomers are engaged in a cosmic treasure hunt, using two primary methods to track them down. The first relies on a prediction from Einstein's theory, gravitational lensing. If a primordial black hole passes directly between us and a distant star, its gravity will act like a lens, bending the starlight and causing the star to temporarily brighten. By monitoring millions of stars for these characteristic flashes, we can potentially catch a black hole in the act of crossing our line of sight. The second method hunts for their dramatic finales. A primordial black hole with a mass similar to a large asteroid would be reaching the end of its life through Hawking evaporation right now. Its final death scream would be an intense burst of high-energy gamma rays. Powerful telescopes scan the skies for these telltale explosions, hoping to catch the last gasp of a universe that has lasted since the beginning of time. The implications are staggering. If we find them, it would mean that a significant portion of the matter in the universe is not made of exotic particles, but of these ancient gravitational fossils. It would mean that the darkness holding galaxies together is, in fact, punctuated by countless tiny points of even deeper darkness, a remnant of the universe's first and most violent instant. The line between a cosmic cinder and an eternal prison is drawn by a single critical number. For a star to leave behind a black hole, its dying core must cross a threshold of mass so absolute that nothing can counter its gravitational collapse. This boundary is guided by the Tolman-Oppenheimer-Volkoff limit, the final successor to a concept known as the Chandrasekhar limit. The original Chandrasekhar limit, named for the brilliant astrophysicist who discovered it, defines the maximum mass a stable white dwarf star can have. It is approximately 1.4 times the mass of our Sun. If a stellar core remnant is below this limit, electron degeneracy pressure, a quantum force exerted by packed electrons, can support it against gravity, creating a white dwarf. But if the core is more massive, gravity overwhelms the electrons, crushing the core further. For cores between about 1.4 and 2.1 solar masses, a second line of defense emerges. The collapse squeezes protons and electrons together to form neutrons, and a new quantum pressure from these densely packed neutrons takes over, creating a neutron star. The Tolman-Oppenheimer-Volkoff limit, often around 2 to 3 solar masses, is the final gatekeeper. If the collapsing core exceeds this critical mass, even the fierce resistance of neutron degeneracy pressure fails. Nothing in the known universe can stop the implosion. The core collapses indefinitely, birthing a black hole. Yet these limits are not simple numbers on a page. The final outcome of a star's death is a dramatic, chaotic battle, and the precise mass required for a black hole is one of astrophysics' great uncertainties. The core is not collapsing in empty space. It is a maelstrom of unimaginable density and temperature, and its fate is decided in a fraction of a second. Two mysterious forces play a decisive role in this cosmic dice roll. The first is the ghostly neutrino. During the collapse, trillions of these nearly massless particles are generated. For a brief moment, they are trapped inside the core, and their outward pressure can actually help blow the star apart in a supernova explosion, potentially leaving a neutron star behind. But if the core is too massive, or if the neutrinos cannot transfer their energy outward effectively, their push is insufficient, and the collapse continues unabated into a black hole. The second wild card is rotation. A spinning core possesses angular momentum, and as it collapses, it spins faster, like a figure skater pulling in her arms. This rapid rotation can provide centrifugal support, potentially halting the collapse and creating a neutron star, even if the mass is theoretically above the limit. Conversely, if the rotation is misaligned or instabilities develop, it can actually hasten the collapse. We are left with a profound mystery. The birth of a black hole is not guaranteed by mass alone. It is a complex ballet of nuclear physics, neutrino interactions, and stellar dynamics. A final, violent struggle where a fraction of a solar mass, the direction of a spin, or the behavior of a ghostly particle makes the ultimate difference between a brilliant city of neutrons and an abyss of eternal darkness. That final, violent struggle leaves behind a darkness so complete it should be invisible. Yet, in a triumph of human ingenuity, we have taken a picture of its shadow. The first image from the Event Horizon Telescope was not of the black hole itself, but of its silhouette against a backdrop of incandescent gas, a perfect circle of darkness ringed by fire. This shadow is the black hole's fingerprint, and its precise size and shape reveal profound secrets. The diameter of that dark void directly measures the black hole's event horizon, which in turn tells us its mass with stunning accuracy. For the supermassive black hole in galaxy M87, that shadow confirmed a mass of 6.5 billion suns, a number deduced not from the motion of stars around it, but from the very void it cast. But the shadow is more than a scale. Its shape is a cosmic gyroscope revealing the black hole's spin. A non-spinning black hole would cast a perfectly circular shadow. However, if the black hole is rotating rapidly, its immense spin drags the fabric of spacetime around it, warping the path of light and squashing the shadow into a lopsided, asymmetric form. The slight but detectable flattening of one side of the M87 shadow tells us this cosmic giant is spinning, and the direction of that spin paints a picture of its violent history, likely shaped by the consistent inflow of material from its accretion disk over billions of years. The brilliant ring of light surrounding the shadow, however, holds the deeper, unresolved puzzles. That ring is not a simple, glowing hula hoop. It is the combined light from the entire maelstrom of the accretion disk, with its photons bent into a perfect circle by the black hole's gravitational lens. The brightness of the southern part of the ring in that first image was a surprise, a feature that points directly to the chaotic physics of the disk itself. This asymmetry is a battle between two titanic forces, the ferocious rotation of superheated plasma and the powerful magnetic fields tangled within it. The bright region is likely a relativistic jet in the making, a point where magnetic fields are twisted so tightly that they launch material outward, creating a brilliant hotspot in the swirling chaos. What we still do not know is the exact recipe for this cosmic engine. How much of the ring's structure is governed by the black hole's gravity alone, and how much is dictated by the complex, turbulent properties of the inflowing plasma? Why do the magnetic fields organize themselves to create such a sharply defined ring, and what determines where those bright, jet-launching hotspots will form? The shadow gives us the outline of the monster, but the fiery ring is its turbulent, living atmosphere, a dynamic and violent place where matter is not just falling in, but fighting to escape. Every new observation peels back another layer, forcing us to ask if we are seeing a simple silhouette or the reflection of a far more complex and active beast. That perfect circle of darkness, the black hole's shadow, is a monument to the power of gravity, but the very equations that predict its existence also fail at its very center. The singularity is not just an object, it is a scream from the universe that our understanding of reality is broken. General relativity, which so masterfully describes the large-scale structure of the cosmos, hits a wall of infinities when it tries to describe this point of zero volume and infinite density. It is a clear signal that we are missing a crucial piece of the puzzle, a theory that can marry the world of the very large with the world of the very small. We need a theory of quantum gravity. This would be the ultimate framework, describing how gravity works at the scale of individual particles, where the fabric of spacetime itself might be made of discrete, quantized units. Without it, the singularity remains a mathematical and physical dead end. Several candidates are vying to solve this problem, and each offers a radically different vision for what replaces the terrifying singularity. String theory, for instance, proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. At the heart of a black hole, these strings could tangle together into an immense, fuzzy ball of energy, a structure known as a fuzzball. In this view, there is no sharp singularity at all. Instead, the entire interior of the black hole is filled with this vibrating, stringy material, a quantum entity that has a finite size and a complex structure. The event horizon is not a special boundary, but simply the surface of this giant fuzzball. Another approach, loop quantum gravity, suggests that spacetime itself is woven from a network of tiny, indivisible loops. In this theory, the immense gravitational collapse does not lead to an infinite point. Instead, the crushing gravity is met with an equally powerful repulsive force generated by the quantum nature of space. This results in a quantum bounce. Imagine the collapsing matter reaching a point of maximum density and then rebounding, like a ball compressing against an unimaginably stiff spring and then shooting back out. This could mean that a black hole is not a one-way ticket to oblivion, but a gateway. The matter falling in might not be destroyed, but instead be ejected into a new region of spacetime, potentially giving birth to a new universe. So, is the center of a black hole a place of ultimate death or a moment of cosmic rebirth? Is it a featureless point of infinity or a vibrant, fuzzy ball of quantum strings? The answer will only come from a theory that successfully unites the force that shapes galaxies with the rules that govern atoms, finally silencing the scream of the singularity with a deeper, more complete song of the cosmos. The equations that govern black holes may hide a startling secret, one that connects them to the most advanced concepts in computing. A theoretical discovery suggests that black holes could act as cosmic memristors, a special type of electrical circuit component with a built-in memory. In an ordinary circuit, a resistor simply opposes the flow of current, forgetting everything the moment the power is switched off. A memristor is different. Its resistance changes based on the history of the current that has passed through it, allowing it to remember its past state even after the power is gone. It is a fundamental circuit element that learns from its own experience. Astonishingly, when physicists analyze the behavior of an event horizon under the flow of energy and matter, the equations of general relativity produce a relationship identical to that of a memristor. The black hole's horizon appears to adjust its properties based on what has fallen into it, not in terms of mass or spin, but in a more subtle, information-rich way. It is as if the horizon itself possesses a form of cosmic memory, its very fabric altered by the history of its consumption. This is not a physical circuit you could probe with wires, but a fundamental property emerging from the geometry of spacetime under extreme conditions. The implications are staggering. If true, it suggests that a black hole is not just a simple gravitational pit, but a dynamic information processing system. The memristor behavior hints that information might not be statically painted on the horizon like a hologram, but could be actively processed and integrated over time, with the black hole's past directly influencing how it interacts with its future. Could this memory effect be the mechanism that finally preserves information, solving the paradox that has haunted physics for decades? Or does it point to an even deeper role for black holes, not as endpoints, but as computational nodes in a vast cosmic network, processing the very data of reality itself? This discovery blurs the line between gravity, information, and computation, leaving us to wonder if the universe's most destructive objects are also its most sophisticated libraries. This cosmic library, with its memristive memory, forces us to reconsider the very dimensions of reality. The holographic principle is perhaps the most radical idea to emerge from the black hole information paradox. It proposes a stunning simplification of the cosmos, suggesting that all the information contained within any volume of space, including every star, planet, and person, is not stored throughout its three-dimensional interior. Instead, it is perfectly encoded on its two-dimensional boundary like a hologram. A hologram is a two-dimensional surface that, when illuminated with light, projects a flawless three-dimensional image. The holographic principle asserts that our universe might work the same way. The world we perceive, with its depth and solidity, could be a magnificent projection from information stored on a distant cosmic surface. Black holes are the ultimate evidence for this mind-bending concept. The Bekenstein-Hawking formula showed that a black hole's entropy, which is a direct measure of its information content, is proportional only to the area of its event horizon. The amount of data a black hole can hold does not depend on the vast volume inside it, but solely on the two-dimensional area of its spherical surface. Think of the universe as a room. You would naturally assume that the amount of stuff you can fit into the room and the complexity of how you arrange it depends on the room's volume. A bigger room holds more furniture, more books, more intricate possibilities, but a black hole defies this logic. A black hole with twice the radius has 8 times the volume inside, yet its information capacity only increases by a factor of 4 because the area of its surface only quadruples. It is as if every book, every atom, every memory that falls into the black hole is not lost in the dark interior, but is instantly translated into a code and painted onto the inner surface of the event horizon. The three-dimensional object is transformed into a two-dimensional description, and the universe we see is just a reading of that description. This principle, if true, redefines the nature of existence. Are we and everything we see just shadows on a wall? is the rich tapestry of our three-dimensional reality and illusion, a cosmic projection whose source code is written on the boundary of space. Black holes are not just testing this idea, they are screaming its truth. They are the universe's way of showing us that the deepest layers of reality are not made of stuff, but of information, and that information prefers to live on the surface. That shadow's lopsided shape is a permanent record of a relentless cosmic spin. The mystery of black hole rotation asks how these gravitational giants acquire such incredible rotational energy. A newborn black hole inherits the spin of the star that collapsed to form it, a final whisper of the star's own rotation amplified to an unimaginable degree. But that is only the starting point. The true spin is built over millions of years by the material it consumes. Imagine a figure skater pulling in her arms to spin faster. As gas, dust, and even entire stars spiral inward from the accretion disk, they carry their own angular momentum, transferring it to the black hole and causing it to rotate ever more rapidly. The most dramatic spin increases come from violent mergers. When two black holes spiral together and collide, the resulting single black hole can be sent spinning at a significant fraction of the speed of light, its horizon whirling with the combined angular momentum of the original pair. Yet physicists are still debating if there is a maximum possible spin. General relativity suggests a theoretical limit, a point where the black hole would be rotating so fast that its event horizon would vanish, exposing the dreaded naked singularity. But the universe seems to prevent this, perhaps through processes that radiate away excess energy, keeping the spin just below this cosmic speed limit. This spin is not just a curious detail, it is a primary source of power. A rotating black hole drags the fabric of spacetime around with it, creating a whirlpool of energy just outside the event horizon. This region, the ergosphere, is where the black hole's rotational energy can be tapped. Matter and magnetic fields get caught in this cosmic whirlpool, and through mechanisms like the Blandford-Zenagic process, some of that immense rotational energy is channeled and launched into the universe as those blisteringly powerful jets. The spin directly dictates the engine's output, influencing how brightly the accretion disk glows and how far the jets can penetrate into intergalactic space. An unanswered question remains: why do some supermassive black holes, like the one at the heart of our own Milky Way, appear to be slow, quiet spinners, while others, like the one in Galaxy M87, are rapid rotators powering colossal jets? Is it a matter of diet, a history of chaotic, random accretion versus a steady flow of material? Or does it depend on the black hole's violent history of mergers? The spin of a black hole is the story of its life, a hidden record of everything it has ever consumed and every collision it has ever endured, written in the twisted geometry of spacetime itself. That cosmic spin is a force that shapes entire galaxies, yet it is dwarfed by the invisible presence of dark matter. The 27th mystery dares to ask if these two great cosmic enigmas are secretly linked. Black holes and dark matter, one an all-consuming darkness and the other a ghostly, unseen mass, might be locked in a hidden dance that dictates the structure of the universe itself. One compelling theory suggests that supermassive black holes act as powerful anchors for dark matter. Imagine the black hole's immense gravity acting like a cosmic magnet for the mysterious particles that make up dark matter. As these particles swarm around the black hole, they could be pulled into an incredibly dense cloud, a sharp spike of concentrated darkness right at the galaxy's center. Within this dense spike, the dark matter particles could be colliding with each other at tremendous speeds. According to some models, these collisions would cause the particles to annihilate, transforming their mass into a burst of gamma rays and other high-energy particles. This would make the region around a supermassive black hole glow with a faint, unnatural light, a telltale signal of dark matter's presence. Our most powerful telescopes are now scanning the hearts of galaxies, searching for this specific high-energy signature emanating from the vicinity of black holes. Finding it would be a monumental discovery, finally revealing the identity of the universe's dominant form of matter. Another profound possibility concerns the black holes we cannot easily see. Dark matter is thought to form vast spherical halos around every galaxy. Could these halos be hiding a population of intermediate mass black holes, the missing link between stellar mass black holes and the supermassive giants? These hidden black holes, with masses of thousands of suns, would not have the bright accretion disks that make their larger cousins visible. They would drift through the dark matter halo like invisible sharks, their presence felt only through their subtle gravitational influence. They could be the seeds from which supermassive black holes grew, and their gravitational tug might be the hidden hand that helps sculpt the early structure of galaxies, guiding how ordinary matter clumps together to form stars. This deep connection forces us to reconsider the very nature of cosmic evolution. Perhaps dark matter is not just a passive backdrop. It could be an active participant, its distribution and behavior fundamentally shaped by the black holes it surrounds, while simultaneously governing the growth and placement of those very same black holes. Are we looking at two separate puzzles, or are we seeing different pieces of a single, unified picture of how darkness builds the cosmos? The violent mergers of black holes send shudders through spacetime, ripples we detect as gravitational waves. Yet some physicists are listening for something more, a faint whisper hiding in the aftermath of these cosmic crashes. They are searching for gravitational wave echoes, and their existence would shatter our classical picture of the event horizon. According to Einstein's general relativity, the event horizon is a one-way street. When two black holes collide and merge, the new, larger black hole rings like a bell, emitting gravitational waves in a clean, damped signal that smoothly fades away. This final ring-down is the sound of the event horizon settling into its new, calm shape. But if the horizon is not a perfect barrier, if it is actually a fuzzy quantum structure or has a hard, reflective surface just outside the classical boundary, then the story changes dramatically. In this scenario, some of the gravitational waves produced in the merger would not escape immediately. They would bounce against this quantum wall, trapped briefly between this exotic surface and the outer edge of the gravitational potential. Each time a wave reflects, a tiny fraction of it leaks out, creating a series of delayed, fading copies of the original signal. These are the echoes, repeating murmurs that would arrive at our detectors long after the main crash has subsided. The debate over these echoes is fierce. Several teams have reanalyzed data from the LIGO and Virgo observatories, claiming tantalizing evidence for these repeating signals hidden in the noise. They point to statistical correlations that seem to align with predictions for a quantum structure at the horizon. For these researchers, it is a potential revolution, the first experimental hint that the event horizon is not the smooth, featureless membrane of general relativity, but a physical entity governed by quantum gravity. The skeptics, however, remain unconvinced. They argue that the alleged signals are too weak, that they could easily be random fluctuations in the detector's background noise, glitches masquerading as physics. They have performed their own analyses and found no significant evidence, accusing the other side of cherry-picking data. The community is divided, with both camps refining their methods and awaiting more sensitive data from future observing runs. If these echoes are real, their implications are profound. They would be direct evidence of physics beyond Einstein, a glimpse of the quantum nature of spacetime itself. A confirmed echo would mean the event horizon is not the final word, that there is a dynamic, reflective layer just outside it, perhaps a firewall, a fuzzball surface, or something entirely new. It would mean that the black hole's interior is not an inaccessible void, but a region whose presence can be felt through its interaction with the waves bouncing against its quantum gate. We are left waiting for a clearer signal, a louder echo that rises unmistakably above the cosmic static, one that could either solidify a new era of quantum gravity research or silence a beautiful, controversial idea forever. The fate of every black hole is a slow, cold whisper in the dark. Across trillions upon trillions of years, as the last stars flicker out and galaxies drift apart into an ever-expanding emptiness, these cosmic giants will begin to fade. The relentless leak of Hawking radiation, a process almost negligible today, will become their dominant story. One by one, they will shed their mass, shrinking ever so slowly at first, and then in a final, furious burst of light and particles, they will vanish from existence. This evaporation poses the most profound question of all. When the last black hole is gone, what remains? Is the universe left as a perfectly empty, featureless void, a silent and eternal graveyard? Or is there a permanent scar, a ghostly imprint of what once was? The answer hinges entirely on the fate of the information they consumed. If that information is truly and irrevocably lost in the final flash, then the universe itself suffers a form of cosmic amnesia. The history of every star, every planet, and every civilization that ever fell into a black hole would be erased from the fabric of reality, a fundamental loss of the universe's own memory. The cosmos would be left not just cold and dark, but fundamentally incomplete, its past partially destroyed. This violates the core principle of quantum mechanics, which insists that information can never be destroyed, only transformed. Yet if the information does escape, perfectly encoded in the last pulse of Hawking radiation, then a different, equally staggering future awaits. In that final flash, the black hole would not just be disappearing, it would be speaking. It would broadcast a complex, encoded message containing the entire history of everything it ever consumed. The universe would be filled with these last testament signals, a cosmic library of faint, fading broadcasts from long-dead gravitational giants. This preserved information could have consequences for the very structure of reality on the largest scales. Some theories suggest that this endless cycle of information preservation and recycling is what allows for the possibility of new universes to be born from the ashes of the old. In this grandest view, black holes are not merely endpoints but cosmic engines of rebirth. Their life and death could be part of a vast, cyclical process where the information from one cosmos becomes the seed for the next, ensuring that nothing, not even the universe itself, is ever truly lost, only transformed in a cycle of cosmic renewal that spans eternity. The final mystery brings our cosmic journey down to Earth, to the tunnels of the world's most powerful particle accelerator. Scientists at the Large Hadron Collider are not just smashing protons to discover new particles, they are probing the very fabric of spacetime, and in doing so, they are flirting with the possibility of creating a microscopic black hole. This is not the planet-devouring monster of science fiction. It would be a tiny, fleeting entity, smaller than a single atom, born from the incredible energy of a collision. The principle is one of ultimate concentration. When two protons traveling at 99.9999991% of the light speed collide head-on, their energy is squeezed into a volume a million times smaller than a mosquito. According to Einstein's equations, energy and mass are equivalent, and such an intense concentration of energy can, in theory, warp spacetime so severely that it pinches off, forming a quantum black hole. The immense scientific value of such a creation would be incalculable. Detecting its instantaneous evaporation through Hawking radiation would be the first direct proof of that famous theory, confirming that black holes are not eternal. It would open a direct window into quantum gravity, allowing us to study the laws that govern the singularity in a controlled, observable way. The energy required to create such a black hole in our familiar 3 dimensions of space is far beyond the reach of any machine we can build, a staggering 100 million billion times more powerful than the Large Hadron Collider. This is where the theory of extra dimensions offers a breathtaking shortcut. String theory suggests that the universe may have more than the 3 spatial dimensions we experience. These extra dimensions could be curled up, hidden from our everyday perception. If they exist, gravity, which we perceive as exceptionally weak, could actually be as strong as the other forces, but its power is diluted as it leaks into these hidden dimensions. The consequence is revolutionary. In a universe with large extra dimensions, the energy needed to create a black hole could plummet to a level within the reach of the Large Hadron Collider. The creation threshold is not a fixed number. It is a door that could be unlocked by discovering the true, higher dimensional architecture of reality. This leads to the inevitable safety question, a concern often raised and thoroughly debunked by physicists. Any microscopic black hole created would be extraordinarily unstable, possessing a temperature of over 1 billion degrees. It would evaporate into a shower of ordinary particles in a time span so short it is almost meaningless, vanishing in about 10 to the minus 27 seconds. It would have no time to accrete any meaningful amount of matter. Furthermore, cosmic rays, high-energy particles from deep space, have been bombarding Earth and other celestial bodies with far greater energies than any particle accelerator for billions of years. If such collisions could create dangerous black holes, the evidence would be all around us in the form of ancient, devoured planets and moons. The fact that we exist is the most powerful proof that this process is safe. The true wonder is not the risk but the reward. Success would mean we have not only created a black hole, but we have also discovered the hidden dimensions of the cosmos, all within a 17-mile-long tunnel beneath the French-Swiss border. It would be humanity's ultimate act of cosmic engineering, turning the most destructive force in the universe into a tool for our own enlightenment, proving that the final frontier of discovery might not be in the distant heavens, but right here in the heart of our own machines. From the silent scream of the Singularity to the faint whisper of Hawking radiation, these 30 mysteries form a constellation of our ignorance. We have journeyed from the event horizon's fiery paradox to the holographic surface where reality might be a projection, from the spinning giants that power galactic jets to the possibility of microscopic black holes born in our own machines. Each unanswered question, from the fate of information to the existence of white holes and wormholes, is not a dead end but a frontier. Black holes are the universe's most demanding teachers, forcing us to confront the broken pieces of our own physics and daring us to imagine a deeper, more unified truth. They are the ultimate cosmic laboratories, testing the very limits of space, time, and information. So we turn this final question to you, the explorer. Which of these profound puzzles captures your imagination the most? Is it the terrifying firewall, the promise of a wormhole bridge, or the haunting possibility that we are all living in a hologram? Let us know your thoughts, and if your curiosity for the cosmos is as infinite as a black hole's density, subscribe for more deep dives into the universe's greatest enigmas.